So let's come to next problem. That so let's come to next problem. This is a very interesting problem, and it's involved a lot of calculation. But look at this is the very nice problem. You can see it is given that a person have its body temperature at 35 degree. So it has a body temperature of 35 degrees centigrade, and we have to estimate what will be the maximum, what will be the associated wavelength, uh, which will give the maximum power or maximum intensity. So first question is this, and second question, it is also given that the environment temperature is 20 degrees centigrade, and it is given that human skin has emittance of 0.98. So it is the some parameter that will tell you about how much energy you can absorb or how much energy you can radiate uh, with respect to black body radiation. So always it will be less than 1. So it is given 0.98. So what we have to do, we have to estimate net loss of power from the human body. And second, we have to also calculate the net loss of energy during one day. So we will estimate what will the energy that we can lose every day. So let's go for step by step. The first is all about that we have to just use the Wien's formula, because it is given that lambda maximum is equal to some constant. Let's say this constant is B upon T, and T is the skin of the body. So this will be skin of the body, and we have to calculate each and everything in term of Kelvin. So this will be 35 plus 273, and that will be 8. 3 plus 7 is 0, so 300 Kelvin. So from here we can get the value, and that will be lambda is equal to 2.9 into 10 to the power minus 3 Kelvin meter upon 308. So lambda maximum. So if we are going to calculate, I think this will be approximately 9.5 micrometer. So this is the first question we are just going to do. The second question is very interesting. So first we have to see how much energy the body emit and how much energy it will absorb. So what formula we are going to do? So the total change in power is equal to just power of in power which will be emitted by the body, power emitted by the body minus power absorbed by the body. So we have to calculate delta P. So first let's try to calculate what will be power emit. So power emit is nothing but the epsilon sigma A T to the power 4, and epsilon is 0.98 into 10 to the power, we can calculate all these things. So 10 to the power, sorry, this is 0.98, and sigma is all about 5.67. So 67 into 10 to the power 8. Area is 2 meter square, and here temperature is 308. So we will just go for 308 to the power 4. When we are going to calculate this thing, I think you will get the number 990 watt. So this is the emitted energy by the body, and then we will just go for that absorbed energy. So absorbed energy is equal to again sigma, and this is the skin body. So this is the skin. So sigma epsilon A T to the power surrounding to the power 4. So this is the temperature you can find from the surrounding. So we can just put again 0.98 into 5.67 into 10 to the power 8. Area is 2 into this will be 293 to the power 4, because 20 plus 273 is all about 293. And when we are going to calculate it, obviously this will be 803 watt. So what will be change in power? The change in power is 990 minus 803 watt. So this will be approximately, I will get 187 watt. So this is the power the body will radiate. And now we have to calculate what will be the energy. So we are just going to calculate what will be the energy lost during whole day. So we have to use this space. So in whole day we have total time. So time is given 24 into 3600 second. So this will be the time. So in this time the body will radiate this much of energy. So that will be delta P. So this energy delta E is equal to delta P into T, and delta P is 187 into 24 into 3600, and that will come out of a very large number. You can see this will be 16156800 joule, and we can convert it into calorie. So then this number is 3861 kilocalorie. So this is the number you can just calculate, and you can see this much of energy we are losing every day. We are losing every day uh, without doing any work and anything. So this much naturally this much of energy we are losing. So at least we need some food to overcome this much of energy. So that is different issue. But yes, our body is also radiating uh, the wavelength, but that wavelength is not visible because they are in the range of some micrometer. So I have calculated that is their range of some 9.5 micrometer, and you can see that this type of problem we can also try to understand what is going to happen our body, and how this spectrum can tell about the temperature, and how this temperature is related to all about radiating the thing. And we can also calculate how much energy we can radiate, how much energy we are wasting every day due to just only due to this radiation. So this is the wonderful problem to using a Stephen's law, and particularly wind displacement law. I hope you can just recheck this calculation. I am sure this calculation have done correctly by me, but you can recheck all these things. So next part of questions we will just go to do little bit of question on mainly this uh, Planck's formula, and we will see how we can analyze all kind of things. So let's go for next level of problem.